Okay, thanks for the invitation. It's a pleasure to be back in Regensburg. Yeah, I'm going to talk about some aspects. Well, I was thinking what would be a good topic for a conference on derived algebraic geometry, invertible objects, and duality. So I thought, why not talk about something that makes heavy use of all three of those, namely elliptic homology. And, well, I'll skip the invertibility part for the title, but there will be some invertible objects as well. Okay, so so just basic setup here. Is there a clock in this room? Right, okay. Basic setup, let's take R an E infinity ring spectrum. Okay, and I want to do that because then mod R, this is a stable infinity category, stable symmetric monoidal infinity category. I guess stable is really the least relevant here. So it has a full subcategory of dualizable objects, which in this case we can identify with the compact objects, or aka the perfect objects if you want. But that's special to this situation. And we might ask, how do we obtain elements, obtain objects of this category, mod R dual? Okay, well, I already gave you one clue that compact objects are dualizable. So you could take any retract of a finite cell R module that would give you such an object. But what about the function spectrum R to the X for X a space? So when is something like this dualizable? Well, let's take the case where R is the sphere first. And then, of course, this is asking about Spanier-Whitehead duality. So we know that R to the X is dualizable if X is a compact space. So this will be notation for the infinity category of spaces, and the omega means omega small, so or compact in this case. Okay, so that doesn't really tell us anything. We know what we know what finite spaces look like. They're retracts of finite CW complexes. But on the other extreme, we could go to something like HQ, where then R to the X is dualizable if X is a pi star finite space. So all of its homotopy groups, or sets, as it were, in degree 0, say, I'm going to take to be finite. This is just a calculation. So we can see that we have, as we descend the chromatic ladder down to height 0, we find more and more dualizable things. So let's consider an intermediate example. So what about R is complex K theory? Well, here things start to get a bit more interesting. So we can do a lot of calculations in K theory. For example, we can calculate the K-theory of BG, the classifying space, for, say, G, a finite group. We know that in degree 0, this is just the representation ring of G, which is, completed at the augmentation ideal, which already is going to tell us that, well, this is going to be pretty large as a KU0 module. But if we did the smart thing and instead asked for something that gave us the representation ring itself, then sometimes these are dualizable modules. Ask instead about KU of, well, let me write it like this to distinguish the stack. So this is the classifying stack for principal G bundles. So we know that this is the same as, well, the G equivariant K-theory of a point, which, let's say in degree 0, is the actual representation ring of G, which is free on the irreducible representations. So as long as there's finitely many irreducible representations, this is going to be dualizable Z module, and you can use that to calculate that KU of the stack BG is a dualizable KU module for G, a finite group. So as long as we were careful to define K-theory correctly, now we found a larger class of examples that KU sees as dualizable. Why do we care about this? Well, when we have something that's dualizable, we get transfer maps. We get transfer maps in cohomology along, let's say, maps of spaces. Well, I should expand that a little bit because I already said that we need to consider stacks along maps of spaces or stacks with, let me say, an R cohomology with R dualizable fibers. So that's why we care. We can calculate, so how does this thing work? Oh, so I don't touch that. Oh, right. Okay. Fourth try is a charm. Okay, so it's important for making calculations that we should be able to identify some dualizable objects. Okay, so let me step back and now put this into a bit more perspective. So R, this is a commutative algebra over the sphere, or an E-infinity ring spectrum. Same thing. We can view it as a functor from, when I consider the R cohomology of X, I can view it as a functor to R modules, except that if it's the R cohomology of X, it'll actually have canonically a commutative R algebra structure. And it's a contravariant functor, so I should put an op on one of these sides. And, well, typically the op would go here, but I'm going to put it here just because I'm going to do the same trick that Ben did and define this to be, think of this as affine derived schemes over R. So this is R theory. This is a colimit preserving functor. So because I'm doing the op here, if I have a colimit of spaces, I'll get a colimit of affine R schemes, or a limit of algebras. And, well, we already decided that we should try to enhance our theory to some version of stacks. Now, this is an infinity category of spaces, so I have to be very careful what I mean here. I need some infinity category of topological stacks, which I'll say a few words about in a moment. So inverting some weak equivalences is going to turn that into an actual infinity category, which receives a fully faithful map from here. And, well, for some purposes, it might be useful to also enlarge the target category of where we're taking values. And this, well, there's a natural thing that affine R schemes embeds into, which is sheaves on affine R schemes. Or I'll just write sheaves over R for simplicity, by which I mean this is some sort of category of functors from affine R schemes op into spaces, satisfying some descent conditions, which is not so important for this. Now, we have this thing there's a map going back, which is taking the global sections, or the affinization map. So let me just say there's a global sections map from this sheaves on commutative sheaves here down to this. Let me put an op there. So if it were affine, it would just send spec of A to A. And then it extends that, well, any sheaf here is a colimit of representables, so I can then extend that functor formally. What that gives me is a map going back, which is for which this is a section. So I can always view my homology theories as taking values there and then applying global sections to it. So this is Yoneda. This is global sections. And now what I've claimed that I can do for K-theory is actually find a functor here, which is going to take some stack and give me some sheaf whose then associated cohomology I'll obtain by taking the global sections of that sheaf. So let me give you an example. So for, well, let me maybe say more about what this is and how we can create such functors. So the first thing that I want to talk about is what this category really is. This is what Schwede calls the unstable global homotopy category. And it has a very, it has a nice presentation. What we need to construct it, we need two things. So we need, well, three things. So we need a mapping stack. That's saying that stacks are enriched over themselves, so I have a stack of maps between any two stacks. I need a homotopy type of a stack. And I need some objects which will be generators. And if I have this, then what I can do is I can define then a functor from stacks into, well, so maybe I should say what these are. So if I have two stacks, x and y, I have just a stack of maps from x to y, just given by the fact that this is a Cartesian closed category. If I have a stack x, I have its homotopy type, which is, defined by x goes to, well, it's the realization of this simplicial groupoid. I can take x, I can evaluate it on the spaces delta n, and I can geometrically realize. This gives, it's kind of like a weak homotopy type. And the generators will be the same things that we use, say, in equivariant homotopy theory. They'll be what are called the orbits, BG. And here, I'm going to restrict G to be a compact Lie group. And with these three ingredients, I get a functor from stacks to functors from this orbit category op to spaces, which I'm going to think of as stacks with some weak equivalences inverted. That can be made more precise, but I'm not going to do that right now. This goes back to, well, this result goes back to a result of myself with Andre Henriquez. Where we show that this is a well-defined homotopy theory of stacks, and then Stefan later checks that it agrees with his unstable global category. But it just is given by the simple formula. X is going to be sent to, well, I'm going to take my orbit stack, which is BG, and send it to the space of stack maps. In other words, the homotopy type of the mapping stack, x to the BG. Okay, so this is not sending x to its underlying homotopy type. This is only applying the homotopy type to the mapping stacks. So instead of viewing stacks as being enriched over itself, I view it as being enriched over spaces in this way. So you can calculate from this. It's easy to calculate what what this orbit category looks like. Maps in this orbit category from BG to BH are HOMs from H to G, and then you take the homotopy quotient, sorry, G to H. Then you take the homotopy quotient by the action of H, which acts by conjugation. So in particular, if I have something which is abelian in the target, like the circle, so bold T will be the circle here. This is just the characters of G cross, well, because this is abelian, it acts trivially by conjugation, so I get cross the space BT. So this is just a special case, but I want to focus on what happens to this particular stack. And you can see that what this formula is saying is describing the homotopy type of this stack. So this is a topological or a smooth stack representing principal T bundles. And to understand its homotopy type in this homotopy theory here, you just have to know what maps from other orbit stacks into it are. And it's just given by this formula in this case. I give say a smooth group homomorphism from G to T, and then a point in CP infinity. Okay, so so that's what I'm going to put on this side. And we can now use this. So I'll write this. I'm going to give this category maybe a new name, S sub orb, for the global unstable category, because it's just pre-sheaves of spaces on this orbit category. So we have S, it sits inside, spaces sits inside this homotopy theory of stacks just by the usual viewing a space as a discrete stack. And now I want to construct some functor, which maybe I'll call phi or something, to some algebraic world where I have a version of sheaf cohomology. So say sheaves over R in some topology, let's say the Étale topology. And with that, then I can take global sections to go down to, commutative R algebras, say op. And well, I could expect that this reconstructs my original R theory functor, but enhances it to things that I wasn't traditionally able to take the R theory of. So how can I construct such a functor then? Well, I don't want to construct just any functor, but I want to construct a functor that'll allow me to do calculations. So what's going to give me calculational control over such a thing? Well, what I'm going to want is I'm going to want my functor to at least preserve colimits, so I can do cellular arguments. But I'm also going to want it to preserve finite limits so that I can keep control over fibrations that exist in my categories. So in order to get a good calculational control over a functor like this, for which I'm going to then apply global sections to get down to spectra, or yeah, I'll just say mod R op. Of course, there's really more structure there, but this I can calculate using the descent spectral sequence. Okay, so this is traditionally how people make calculations in derived algebraic geometry. For example, if you need to know the global sections of a sheaf F, well, in derived world, that's going to be some type of spectrum or R module, and you'll want to be able to calculate its homotopy groups. You use the descent spectral sequence, which goes from the pth cohomology with coefficients in, say, the qth homotopy sheaf of F, converging to pi q minus p of the global sections. So that we can have reasonable control over, provided, provided we can calculate these invariants of a sheaf F. And on this side, what do we need? Well, this is freely generated. This is, after all, functors from the orbit category op into spaces. So this is freely generated under colimits by orbits. So I'm going to, in order to do cellular arguments, I want that this preserves colimits. So in other words, I just have to say where each orbit goes. But in geometric situations, I'm going to have various types of fibrations that I might want to consider here. And I want these fibrations to remain fibrations over here. So I also want, I want phi to preserve colimits, and I want it to preserve finite limits. And for those of you who know, because, well, that way it can fibrations here will become fibrations here. And also then to calculate global sections, I can use the Leray-Serre spectral sequence. So what I want to do is, what I'm asking for is a morphism of topoi. This is an infinity topos. This is an infinity topos. Sorry, not that one. This one. And you don't have to worry about what that is, but the point is they're nice categories that look like sheaves on something, and the geometry that topos, the internal geometry of that topos is preserved when you consider functors that preserve colimits and finite limits. So this reduces the question to find morphisms of infinity topoi from this thing, S orb, to sheaves over something. I'll take a basic, some geometric object, and I'll throw in the étale topology. I'll call this phi upper star, because it's going to be the left adjoint of one of those. And from that, then you get what Stefan would call a global cohomology theory. And it's just defined by, I'll call it R. R of x is the global, well, it's the global sections of O of phi upper star of x. So the construction is highly functorial. I mean, this is just, I should say that this is just a paraphrase of Lurie's approach to equivariant elliptic homology. Except, well, I'm not necessarily assuming that this target category has anything to do yet with elliptic curves. But so how can we find? So what I wanted to convince you of thus far was if I can get a morphism that preserves colimits and finite limits, I can get something that I can calculate. And now the question would be constructing such a thing. So we have another topos, which is slightly simpler than presheaves on all the orbits, which is just presheaves on the abelian orbits. So this is functors from the abelian orbit category to spaces. So this is like the homotopy theory of stacks, all of whose stabilizers are abelian. And, well, this morphism preserves colimits and finite limits. Its restriction, so it has two adjoints. So that's a morphism of topoi. And now if I could find one that goes to here, I could compose the two and get a morphism like that. Now, what can go to here from here? Well, this has a universal property. So this is the first theorem that I want to advertise. So this is myself and Thomas Nicolaus. Is that this thing, well, classifies what's called oriented abelian group objects. So, in other words, you can imagine what an abelian group object is. I didn't tell you what it means for it to be oriented. I will in a moment. But in the sense that this thing carries the universal oriented abelian group. So let me say which one that is. It's the stack BT in here. Is the universal oriented abelian group. And that means that once I can find an abelian group, an oriented abelian group object here, I automatically get colimit and finite limit preserving morphism, which then I can use to calculate some cohomology. So let me just say briefly what it means to have an oriented abelian group object, because the definition I'm going to give is a little bit different than what Lurie proposes. So let's So specifically, the first thing that is important to note is that you would think that in an infinity category, an abelian group object would be some sort of group-like E-infinity object, which is a valid that is a valid definition, but it's not going to work correctly here. This is already known from the case of K-theory. So an abelian group object in, say, an infinity category C is going to be an object. Here, I'll just write it as a pullback. So C embeds into functors from C-op to spaces, and, well, I'm going to want to enrich its functor of points to abelian group spaces. So this is what an abelian group object is, provided we know what this is. And this is defined just to be the category of simplicial abelian groups with the weak equivalences inverted, or if you prefer, connective HZ modules instead of connective spectra, which would be the group-like E-infinity version of this. Okay, but now the question is, what does it mean? Oh, so for example, BT in my Homotopic theory of stacks is necessarily an abelian group object, because we already did the calculation of what its functor of points looks like. Maps from BG to BT is hom GT cross BT. So this is an abelian group, and this is, well, this is a free abelian group on the pointed two-sphere, if you want. So is canonically an abelian group object. Okay, but what does it mean to be oriented? Well, if I have an abelian group object, it always comes with a section. Let's call it the identity section S. And I can factor this as an epi followed by a mono. Let me just call what happens in the middle a hat. Okay, so this is an effective epimorphism, and this is a mono. And what I want, so this will have an abelian group structure itself, and I want this to be the let's say this is all going on in a topos X, then I want this to be the constant. I want this to be identified with the constant sheaf of abelian groups BT. CP infinity, in other words. So, to describe what is happening more, this epi monofactorization can be given in a slightly different way. If I pull back point, if I do this pullback, I get loops A. This is still pointed. And if I take B of omega A, in my topos, in this, in spaces would just be the connected component of the identity. But in derived geometry, this looks something more like the formal completion of the abelian group object along its identity section. So what I'm really asking is that this thing be equivalent to the constant sheaf BT. And just to check what happens here, what happens when I do that with this stack, well, I map in point, I take the pullback, I get the circle itself, and then when I take the classifying space of that, I get that BT hat is equivalent to the space BT. So think of this as like saying the formal completion of the stack BT is the space BT. And well, this is clearly the constant sheaf represented, the sheafification of that, because it's in the pre-sheaf topos. So a theorem of Lurie then says that, and let me say that this was inspired by a comment of Vitsozi, that one could consider derived elliptic curves. A theorem of Lurie is that the moduli of oriented, and I mean oriented exactly in this way, derived elliptic curves. So let me just explain briefly what a derived elliptic curve is. It's a derived scheme which is an abelian group, and it should be flat over the base, and the underlying ordinary scheme should be an elliptic curve. So the moduli of oriented derived elliptic curves, let's call it M, derived, carries, well, is a derived Deligne-Mumford stack, and it carries an oriented abelian group, which is the universal curve over this derived moduli stack. So from this, yeah.
What's the definition of oriented?
I want this to be a discrete object. BT shoved into the topos by the colimit way. Well, no. It's a choice of an identification with that. It is extra structure. Okay, so now we have these ingredients. We can now actually calculate elliptic homology of various things. And I want to tell you what some of those calculations look like, and in particular, why they're related to duality and invertibility. So let me just state some results now. So first and foremost, we might consider what happens now. So I'm going to use this functor, which goes from the unstable global homotopy category to sheaves over the moduli stack. everything is derived here. And I want to know what happens. So TMF of X is going to be, by definition, the global sections of O of that. And again, we can use the descent spectral sequence to calculate this. But first, so this is a result, well, a result in progress of myself, Leonard Meyer, and Thomas Nikolaus, which says that when you take TMF of the stack BT, what you get is, well, surprisingly, and in contrast to the K-theory case, where the K-theory of this is the representation ring of T, which is not a dualizable KU module, you get rather that it's TMF, in other words, TMF of a point, plus a suspension, which we can pin down to a multiple of 24. It's 1 plus 24 times something of TMF. So this says, in particular, from this you can deduce that the reduced TMF cohomology of this stack is an invertible TMF module. So this is already surprising. There's something that TMF sees as being invertible, which is highly non-invertible over the sphere. And from this, you can also deduce that TMF of BG is a dualizable TMF module for G compactly and abelian. That's not hard. But now the question of what happens to non-abelian groups comes up, and this is really the harder question. We already know that K-theory has transfers for finite non-abelian groups, but TMF has more. So at least TMF has, well, let's just say sees certain nice compact Lie groups. So like UN, ON, etc., as dualizable. And one could conjecture or ask the question, I mean, I don't want to conjecture this because I don't really have any evidence other than past the calculations that I know how to make, but the question is TMF of BG a dualizable TMF module? For all compact Lie groups G. And this I don't know the answer to, but I don't know of any counterexamples. But of course, it would say that TMF has lots and lots of transfers. You could transfer along any map of stacks whose fibers are these gerbs, these G gerbs. OK, I'll stop there.
One quick one.
Yeah.
What did etc. mean? O-U-N, O-N, etc.
Oh, well, like S-U-N, S-O-N.
Thomas has an announcement.
Or not.